combine our patterns with logic. So we can have AND or OR in between our patterns. So that can give us more power to have better pattern matching. Because we can have multiple conditions that apply to the same signature. So in comparison to the PEiD, here is the comparison just between the identification parts between the TitanMist and the PEiD. Of course, this only relates to the user database because PEiD is a program, it has its own internal database which has its own rules. So it's far more complex than the user database user can actually extend. So we are just comparing the databases. So for the TitanMist, you can have complex patterns, and for the PEiD, you can only have the simple ones, which are just wildcards and bit masking. For the PEiD, you have only single direction patterns, and for the TitanMist, as we saw, we can go either direction, we can follow calls or do anything. Now, for the PEiD, we only have one starting point, that's the original entry point, and we can follow, and we can search for our patterns anywhere in the file. But we said that's not good enough because files can be big in size and we don't want to waste our time scanning the entire file. That's why we added more starting points for our signatures. So we can either seek or match patterns with the TitanMist. We have variable byte patterns. We can skip some bytes. We have optional patterns. We can follow the code flow. And we have signature priority. So that's the difference between our project and what's publicly available now. So of course, that was the identification part. TitanMist also has embedded unpackers in there. So the TitanMist unpackers are automated. That means no user interference whatsoever. So you don't have to click around, follow, just input some fields or whatever. The unpackers are automatic. So they can be written in any kind of language. So they can be written in C, C++, Microsoft Assembler, Delphi, Lua, Python, and TitanScript. So this only refers to the unpackers that are written based on the TitanEngine. Because you can plug in any kind of unpacker to this kind of project, you can write the unpacker in any kind of programming language or any kind of framework. But since we created the TitanEngine, we based our project on top of that. Now the TitanScript is our version of OllyScript. Now OllyScript is a very popular tool with reverse engineers. We know about 800 different scripts that do unpacking for different kind of formats. We have some duplications of course, but there's obviously a good user base for that. And that's why we added the support for that as well. Now the difference between the TitanScript and the OllyScript is that the TitanScript runs inside the TitanEngine. So it's based on our automated unpacking tools, and it also enables you to use all of the TitanEngine features directly from the script language. So you can use you can easily write unpackers with the TitanScript if you know the TitanEngine. Or if you don't, you can use the OllyScript instructions, and we're going to see how we can convert one of those unpackers easily from the OllyScript to TitanScript. Now here is how TitanMist unpackers look like. You can have native ones, which can be both static and dynamic in nature. It depends on the unpacker itself. You can have the script unpackers, that's Python, Lua, and TitanScript, Python and Lua, and they can be both static and dynamic. It depends on your coding style. And for the TitanScript, there are only dynamic unpackers because OllyScript was created to be assistance during manual analysis of the file. So once you load the file in Olly, you start the OllyScript, and it will get you to the entry point. That's why with the TitanScript, you can only write dynamic unpackers. Now currently there's no DLL support, but with the next release there will be one. So how do you create unpackers? You can create both static and dynamic unpackers, as I said, but the process of creating them has the same steps as the manual analysis, which is debugging the file till the entry point, dumping that memory to disk, collecting all the data you need for import and relocation reconstruction, and then you apply custom fixes for all of the protection options that are available today, such as cold splices, entry point obfuscations, stolen entry points, and whatever the protection options are available inside the format you are unpacking. So the static unpacking also has the same steps. You always must decrypt or decompress the memory content and then reconstruct the import table and the original entry point. Now that's all up to unpackers. whoever writes the Unpackers have to deal with all of this. But there are some shortcuts. We're going to talk about that. So if you are familiar with this slide, it's because this slide is from the last year's TitanEngine, and this describes how you write Unpackers, dynamic Unpackers with the TitanEngine. So what you do is you read the data from the file, and then you initialize the debugging process, setting some breakpoints which collect all the data about import fixing, relocation fixing, and at the end entry point as the final breakpoint which finalizes the unpacking process. So for import data gathering, you would place a breakpoint on the pieces of code inside the packer which calls load library to load a new dynamic link libraries needed by the packed file. So once you are there, you collect the data, and that's just the string, the name of the dynamic link library which is being loaded. That information is passed to the TitanEngine, its importer module, which uses that to reconstruct the import table later. So the same goes for the getProc address, which is the function inside Windows, which finds the functions inside the loaded libraries. So that information as well is passed to the TitanEngine, which at the entry point, at the final point of unpacking the file, reconstructs everything by using that data you collected. Same goes for relocations. Now there's a shortcut because relocations can be tricky to fix. We created a shortcut which is just creating two snapshots. One before the actual relocations occur, and one just after relocation occurs. So once we compare two snapshots, we get a valid relocation table, and that's an easy way to fix dynamic link libraries, which when they have a valid relocation table, they can be loaded on different image bases, and that means that they're valid files for later on analysis. So at the entry point, this is the final step, we have to dump the process to disk, and of course we can use an option to recover the damaged PE header if you like. That goes before the process dumping, and after that we just add a couple of sections, one for the import address table and one for the relocations, after which the file is valid on the disk, but we still need to realign it, which makes it as compact as possible and makes sure that all the sections are in the right place. So once we finish that, we just stop the debugging process because we are done. So that's the whole philosophy, and it's pretty easy steps into unpacking anything with the TitanEngine. Now, as we said, you can create native Unpackers, and I just talked about how you can use the TitanEngine to do this, but you can also create script Unpackers as well. And to create script Unpackers, you can use TitanScript. Now, TitanScript, as we said, is our version of OllyDBG script, so it has the same syntax, but it also enables you to use the existing TitanEngine functions. Now, all these scripts that are existing in the wild, as I said, there are 700 different or 800 different scripts we know about. You can easily reuse them, but you can either recode them or add some instructions to them to make them a valid automated unpacker, because all these scripts are not full-blown unpackers. They will only fix the file and get you to the entry point. At that particular time, you have to dump the memory yourself and fix the import table with additional tools. Now, the TitanScript enables you to create automated unpackers, so those scripts are full-blown unpackers. Now, as I said, we can either recode all these scripts to match the TitanEngine layout, or we can add a couple of instructions. Now, first instruction we can add, and this is really easy, is called dump and fix. So it does what it says. Once you're at the entry point with your script, you just dump and fix the file to disk, and that's all you do. And if there are some errors during unpacking, because this is an automated tool and it needs to know if your actual unpacking has succeeded or not, you can just say, okay, error, this unpacker didn't work. So here is an example of the script. The left one is OllyScript and the right one is TitanScript, and there's just one instruction we added. And this script is a UPX example, so what this script does in way too many lines of code is it finds the pop-add at the end of the UPX stub, places a hardware breakpoint there. Once it breaks, it clears it, and then steps over that, and it's at the entry point. Now, the TitanScript that would do the same thing is exactly the same as this one. So since we are converting OllyScript to TitanScript, we just need to add one instruction. So once we are at the entry point, just before return the end of the script, we just say dump and fix, and that particular script will be executed till that point, and once you're at the entry point, everything from memory will be dumped to disk and fixed by the TitanEngine, TitanMist. So since all of the unpacking we do is either static or dynamic, but we want to rely on dynamic unpacking more because it's a more resilient form of unpacking, that yields a couple of problems. That yields a problem of damaged and broken files that cannot be unpacked because they cannot be started in Windows. We're going to show that a bit later. So we also have problems with files that have missing dependencies, which cannot be unpacked. So if you have a file which is loading a file which dynamic link library which isn't on your system, if you are to unpack that file dynamically, you cannot do that because Windows cannot find it. And there's a problem with some packers which are not data execution protection compatible, so those cannot be unpacked as well. That goes for the packers that store their code inside the portable executable headers, so that's FSG, and there are more examples of this. But there's some good news. There's a solution to all of these problems. We can repair the damaged files, and we can simulate the missing dependencies, so the system thinks that the files are there, so it only gets us through the packing layer, and that's all we are interested in. Once we see the code, we can analyze it further, and if we are into malware analysis, you can determine if the file is malicious or not. And we can just work around data execution prevention or disable it totally. Now, with the TitanEngine, if you follow our blog, we did some series of blogs that describe how we created this plugin, which counters all of these problems of dynamical analysis or dynamic unpacking. So we included this inside the TitanMist project. So if you come across a file which is damaged or broken, you can just use this plugin automatically to unpack the files which other ways cannot be unpacked. Now, the Nexus plugin fixes broken files because validation is a crucial point for any kind of unpacking, especially dynamic unpacking. So before any dynamic unpacking is performed, you really want to do validation. And validation will tell you if the files are broken, and if they are broken, if they can be fixed. Now, as I said, Nexus plugin is included with the TitanMist, and all of this validation and repair is done automatically. Now, the Nexus also solves the problem of missing dependencies. Now, some files load dynamic link libraries through the import table, so those files cannot be started at all, while others can load dynamic link libraries on the runtime, and some of them can actually get through the packing layer automatically. So FSG, for example, if it doesn't find the dynamic link library, it will just continue running, and that's bad because the programs can crash if they're packed with that kind of packer. Others are better at this, and when they don't find the library, they just exit. So to counter this, we can fake the presence of dynamic link libraries both statically on disk, just by creating the files so they are physically there and they have all the exports that are needed by the application. Or we can just hook some functions inside the packed process and return fake values to tell the packer that the necessary dynamic link library and the functions are actually there. So we can do either of those, but the Nexus does both of those because there are different models for different packers, and we want to support everything. Now that brings us to our demo. Now we're going to show the demo, and we're going to show how the TitanMist works. We gave our sacrifice to the demo goats, so I'm hoping they're not going to abandon us now. So we have some samples there. We have one file which is broken. We have files that are packed with different kind of packers, which we have Alex Protector, we have ASPack, we have EXEFog, we have TLock, we have Yoda Crypter, we have Unpack, UPX, and we have some other settings with the UPX as well. So this file, for example, and I just talked about the Nexus plugin, this file, for example, doesn't load because it has missing dynamic link libraries, and we can just see that if we place a breakpoint at the load library call and just see how it works. So the first one, kernel, is found, and then we just scroll till we found the one which is missing. So that's going to be 0. And it ends. So we can unpack that file with the help of the Nexus plugin. So this is the TitanMist. It's a console application that you can call with certain parameters. First one is the input parameter, which tells it which file you want to analyze.